Now, let's discuss that the posterior distribution, which represents our updated belief, is proportional to the product of the prior distribution and the likelihood function. This means the posterior reflects both the initial beliefs encoded in the prior, and the information gained from the observed data, captured by the likelihood. Let's understand that the posterior distribution encapsulates all knowledge about the parameters after we've incorporated the data. Analyzing the posterior allows one to make inferences, predictions, and decisions based on the combined prior knowledge and observed evidence. Now, let's consider credible intervals, which define a range of values where the parameter is likely to fall with a specified probability. For instance, a 95% credible interval suggests there's a 95% chance that the true parameter value lies within that range, offering a measure of uncertainty. Now, let's explore the posterior predictive distribution, which provides the probability of observing new data, given the data already seen. This is useful for forecasting or assessing how well the model generalizes to unseen data. Now, let's discuss that the posterior distribution is the foundation for making optimal decisions. By considering the uncertainty in the parameter estimates, captured by the posterior, decision-makers can make choices that are robust and account for potential risks. Now, let's see that posterior predictive checks are a method to assess how well the model fits the data. Data simulation from the posterior predictive distribution, then comparison to the actual observed data, is performed. Significant discrepancies point to potential model inadequacies. Now, let's understand the sensitivity analysis, which evaluates how changes in the prior distribution or model assumptions affect the results. This is crucial for understanding the robustness of the conclusions. Let's explore that Bayesian model comparison techniques, such as Bayes factors, compare different models to choose the best one. This allows for selection of model that best balances fit and complexity. Alright, let's talk about specifying the prior distribution. This step is about assigning a probability distribution to each parameter in your model before you see any data. It's like setting your initial belief about the parameters. This means the prior distribution represents what you think the parameter values might be before you look at the data. It's your starting point for Bayesian inference. The prior distribution is a probability distribution that expresses your prior beliefs about the parameters. It's your starting guess about the parameter values. The prior is often subjective. It can be based on prior knowledge, expert opinion, or a non-informative prior, which represents minimal initial knowledge. Choosing a conjugate prior simplifies calculations. A conjugate prior results in a posterior distribution that belongs to the same family as the prior, making Bayesian updating easier. If the prior is conjugate to the likelihood, the math gets much simpler because the posterior distribution will have a known form. The beta distribution is a flexible distribution defined on the interval 0, 1, making it suitable for modeling probabilities. This notation represents the beta distribution with parameter p*, given hyperparameters alpha and beta, which determine the shape of the distribution. A beta 1, 1 prior is equivalent to a uniform distribution between 0 and 1, meaning all values are equally likely a priori. If you believe the false positive rate is likely low, you might choose a beta distribution with parameters that place more weight on lower values, such as beta 2, 10. Now, let's delve into calculating the posterior distribution. The posterior distribution represents the updated belief about the parameters after considering the observed data. Bayes' theorem is the mathematical foundation for this update. To repeat, the posterior distribution combines the prior distribution, representing initial beliefs, and the likelihood function, quantifying the data's probability given parameter values. The posterior is proportional to the product of the prior and the likelihood. Now, let's explore how to analyze the posterior distribution. This involves extracting meaningful information to answer questions about the parameters and quantify the uncertainty. To repeat, the posterior provides the information needed to estimate the parameters and gauge the uncertainty. This can be achieved through point estimates, credible intervals, and the posterior predictive distribution. Now, let's look at model checking and refinement. It's important to evaluate model fit and refine if needed. This involves checking assumptions, comparing to alternative models, or incorporating additional data. Model checking assesses the model's validity and identifies potential areas for improvement. Model refinement enhances the model by addressing shortcomings revealed during model checking. Clearly stating the specific question is the base. For instance, is the objective to find the odds of a false positive in a spam filter, or to measure the doubt in an estimate of a population mean from sample data? Models describe the relationships between variables through probability distributions. Gaussian, Bernoulli, and Bayesian networks are examples. Parameters are the unknown elements. For example, the mean mu and standard deviation sigma for a Gaussian distribution, and p for the Bernoulli distribution. Data is the evidence. It's utilized to modify views about the parameters. Clearly define the issue and then select a probabilistic model. The model needs to represent the system and also involves pinpointing the parameters to estimate.